My name is Ross Anderson, and today is March 27th, and this is my 2EI4 Project 3 video. First, let's talk about why I chose a NPN BJT over a PNP BJT or either type of MOSFET. So from my understanding, BJTs operate better in high frequency and high load conditions when compared to MOSFETs, and they also generally have a superior linear gain. And since we're meant to have built a linear amplifier, I thought a BJT was appropriate. And furthermore, since BJTs can switch faster and have lower internal capacitances than MOSFETs and are good for low voltage and low power applications, I thought that it would be a better choice for this project. And BJTs also have a higher GM or transconductance than when compared to a MOSFET, because BJTs are current controlled devices, whereas MOSFETs are voltage controlled, and we want a high transconductance for our purposes. And I also chose the BJT because the data sheet seemed easier to read, and when it came time to breadboard it, it seemed like it would be easier to work with. And lastly, it was discussed in class that we should probably use a BJT for this project, and that seemed like a good enough reason for me. Going over what amplifier topology I chose a common collector amplifier because the gain for these is approximately 1 or a bit less than 1, and this is perfect because we are targeting less than 10% attenuation, or in other words, a gain of 0.9 or above. And another reason is because the input voltage can be large and we want to have a full scale voltage of 1 volt. This would be good for our application. So now going over the math behind my design choices, we first needed to find the transconductance. Now this equation up top here was ripped from the formula sheet for the common collector amplifier, right down on the bottom line right here. And we know that Vt, which is the thermal voltage, is going to be 25 millivolts, and our load is going to be 100 ohms, and Vin is equal to 0.5 volts at absolute maximum. So then we can rearrange this to get an equation for the transconductance, and the transconductance is going to be 0.99 Siemens or 990 millisiemens. Now we need to calculate the input resistance seen by the source. And to do this, we can use this equation for gain from the formula sheet as seen here. I've written it in a slightly different way, but it is the same thing, where 1 is going to be the gain. And we know that the gain has to be greater than or equal to 0.9 because of our attenuation constraint. And we know what our S is, what our L is, and what the transconductance is from the previous step. And then we can get an equation for the input resistance, and we can see that the input resistance has to be greater than or equal to 1 kilo ohm to meet our attenuation requirement. And now we can calculate what the input resistance would be for the component values that I've chosen. So I sort of chose the two 10Ks, as you can see here, sort of arbitrarily, but I also knew that these would have to be high enough to meet the 1 kilo ohm requirement, and because these are in parallel, the number is going to get smaller. And 10Ks are also pretty common, and I just have a bunch of them on hand, so it was kind of arbitrary, but with a little bit of thought behind it. But for this our in value here, we can use the equation on the formula sheet for this, where it's going to be r pi blah blah, but we know that r pi is just going to be the load resistance over the transconductance, and we already know the transconductance, so solving this gives us that it's going to be 10.1 kilo ohms, and then plugging that back in here, you can see that for our resistance values that we have chosen, our input resistance is going to be approximately 3.34 kilo ohms, and this is greater than 1 kilo ohm, so our attenuation constraint was met. So now moving on to the LT-SPICE simulation. LT-SPICE has a nice feature for where a lot of generic components, like transistors or MOSFETs, they have vendor-specific parameters. So for example, this 2N3904 was in our component kit, and LT-SPICE already had this built in to the list of components, and as you can see, there is a SPICE model with all the different parameters. For the simulation, I used a transient analysis that lasted for 1 millisecond, which gives me a few cycles given that the input frequency is going to be 10 kilohertz. And if I run it here, measure the input voltage and the output voltage, you can see that it gives me a nice couple of cycles, and I can see that the input is slightly larger than the output, which is what was expected. To determine the gain from this, we can zoom in onto the peak voltage. Just going to get approximately in the bottom left down here, you'll see the numbers come up. I'm just going to punch it into the calculator here. So that's pretty much exactly 500 millivolts. And this is going to be 480 roughly. So we can do 480 over 500. That gives us 0.96, which is above 0.9. So therefore our gain meets the 10% attenuation requirement. Another one of the performance parameters that I can measure is the input resistance that's seen by the source here. So we know that the current along one path will always be equal. So this current that goes through this source resistor here is the same as the current that's going to be in this capacitor and is in the rest of the circuit. So if we use Vn and we calculate the current across the source resistor, it doesn't matter that it's going to be opposite phase, just the absolute magnitude when we find Ohm's law. So using this, let's pick this point here. So this is going to be pretty much exactly 500, and then we can get the current across it. It's going to be approximately absolute value 114 microamps. So Ohm's law, R equals V over I. So we're going to have 0.5 volts over 114 times 10 to the minus 6. That's going to give us an input resistance of approximately 4,386 ohms. And when comparing that to our approximately 3.34 kilo ohms of input resistance, that was from the mathematical derivation, that's pretty close, and I'd call that pretty darn good. And for my second simulation, I did a AC sweep of 10 points per decade from 1 millihertz to 100 gigahertz. So if I run this simulation, you can see that from approximately 100 hertz to 100 megahertz, the slope is pretty much flat at 0 decibels per decade, and this is going to be our midband gain. So in the previous simulation, I did it at 10 kilohertz, so let's choose there. And in the bottom left, we can see that this is going to be approximately minus 0.4 milladecibels for our midband gain. And in the previous simulation, we got a gain of 0.96. So having a gain of 0.955 for the midband gain seems pretty darn accurate. So this is the physical circuit. You can see here that the orange and the blue correspond to the two channels on the scope, where this is the input and this is the output. The waveform input is connected to this yellow wire here, and you have ground and power on the bottom and top rails respectively. So this here is the BJT, the NPN one that I chose. On this little left pin here, this is connected straight to 5 volts. That's the collector. The base is hooked up to this capacitor, and then the 100 ohm source resistor. And then we also have the parallel combination of the two 10Ks here and here, where the 10K on the base is hooked up to 5 volts and the other 10K is hooked into ground. And then on the emitter, which is the output, we have the 100 ohm load resistor, and the output is hooked up to a capacitor to block the DC, but to allow the AC to come through. For my first waveforms measurement, I did a basic voltage versus time graph where I used a 10 kilohertz sine wave because that's going to be right in our nice mid-band gain range with an amplitude of 0.5 volts. And I used some measurements here. I got the peak-to-peak of my input, which is C1, and my output, which is C2, and the frequency is indeed 10 kilohertz. And when I divide these, that will be my gain, and I'll get a gain of approximately 0.98, which is indeed within 10% attenuation, where it would have to be at least 0.9. I also used a spectrum analyzer where I've zoomed it in here, but you can see that it starts at 100 hertz and goes to 10 megahertz. And from the LT Spice simulation, which I'll pull up here, we can see that the midband is going to be from approximately 100 to 100 megahertz, but the AD2 can't go up to that high because of bandwidth issues. So I've chosen a good enough range that's going to be right in the linear region, and it'll have a bit of roll off at the start, which is what you can see at the very start here, where it's going to be going down to -1 decibels. But at about the 10 kilohertz range, if we go over, it's going to be about -0.1 decibels, whereas waveform said it would be about -0.4. So it's actually better than what the simulation predicted. And as you can see, as we go up, it stays relatively close to the 0 decibel mark. So while it is going to have a little bit less output voltage than the input, it's still going to be really close, and it'll be within the 10% attenuation requirement. So from this, I can say that the midband gain is going to be just shy of 0, or in actual gain terms, it would be about 0.988, which is almost exactly the 0.98 that we calculated from the peak-to-peak values. This network graph also shows at amplitude of 0.5 volts that this circuit does indeed achieve linearity. So just to show this a little bit clearer, if I increase it to 10 decibels and -10 decibels, you can see that, but in this range, the gain is going to be pretty much constant, or in other words, linear. So therefore, my circuit is in practice, according to the AD2, pretty darn linear.